Okay, well, thank you very much, Alexander, for inviting me as well. My name is Kaufmann. I'm from Passivhaus Institute in Darmstadt. I'm there since 2000, so about 11 and a half years now. From profession, I'm a physicist, and, well, I will have the task now to show you some projects. So I'm not an architect, but I hope you will feel about these pictures from architecture. But I will explain some of the technical issues. Many of this material I will show you now and in the afternoon is not done by myself. It's clear, well, my colleagues are listed there. And, well, just to summarize, I want to tell you some of the story from the beginning, because it's interesting to hear and to see what we have learned from several steps. And then going into some projects of the schools and so on. Some conceptual studies. What about doing when we need cooling? In very hot climates we need active cooling. In moderate climate we do not, as Thomas has said. Well, in moderate, warm and cold climate you need not cooling, but if you go south and if you go to tropic and subtropic regions you need cooling and dehumidification. So we will have to deal with that. And in the second presentation in the afternoon, I was asked to tell you something about the efforts all over the world. What you need here and there, and I have some of the prepared maps all over the world, and show you in some detail what's going on there. Okay, Wolfgang Feist already mentioned that we have since about 1.5 years prepared this Puzzlepedia. Please have a look there. And by the way, the video of Wolfgang Feist, what I have shown this morning, is not on the CD because it was too late and too large. But you can have it soon as a download or a downstream on this Puzzlepedia website. So just have a look there and look. Well, the other thing was IFA, International Passivhaus Association, as well, available in the net. And, well, you can get member there. And, for example, the New York Passivhaus is an affiliate there, so you can get member to them. And you are a member to the IFA as well. One issue of the IFA is this brochure, what you all have got. If not, there are some extra examples on the desk. Well, this is an end-user brochure. So it's not for experts, but it's for people who you want to convince to get a passive house or to move into a passive house. So it's probably useful for you as you make decisions, or those who make design of houses, that you can explain to your clients, those who live afterwards and work afterwards in your houses, to tell them what's going on. So just have a look there. Well, Passive House Conference, you are invited to come there. The program of the conference is available on the desk as well, so just take a flyer of that and, well, afterwards go to the website. IFA has many, many projects listed, just a selection of that all over the world. Well, Thomas already mentioned that there is not passive house only since 20 years. There were some conceptions available, and a very good example is that from Norway. This is a description of Fridtjof Nansen, who made journeys and expeditions to the North Pole, and he designed a ship, the cabin of this boat, very precisely according to passive house concept. Very good insulation, 3-pane windows, and a ventilation system. Not with a good heat recovery, but he said, well, we have a very small cabin, 10 people there or 15. We need fresh air, and so we have to do something for the fresh air. Well, and if you read that, that's on the CD, by the way, I will not go into detail with that. If you read that, you see it's very nearby the passive house conception. Okay, this just an example out of history that we are not the very first doing that. Well, now just a list of our learning curve. This is ours. I will tell you and show you this project of 1991 and 2000 and so on, the very beginning. And then a learning curve of a housing company in Frankfurt. And I do this in more detail because it's a good example as well for you in the army. You have to convince other people to do that. You have to convince your bosses to get money for this project and so on. So, well, I will go just into detail and tell you what we have learned from this development. Well, the first house you have already seen, designed by Bott, Riedermeier and Westermeier as architects and by Wolfgang Feist as the scientist. It was an experimental building on that time, so it was quite new. Nobody had it before. Well, and the first 10 years, they had about some 100 visitors every year looking there. And this is a very important thing. You should have maybe small projects ready to show it to the public, to show it to other people, because with buildings, people want to have hands-on. Yeah? It's not enough to have theoretical calculations and so on. Maybe scientists will believe you, but real engineers, even engineers, but as well users living and working afterwards there, they want to see that it works practically. And therefore, you need an example building. Well, and this was the first one. The second project, or a larger project in about 2000, was this Cepheus, as well available on the web, on this acronym. It was an EU-funded project with 200 dwelling units all over Europe, most in Germany and Switzerland, but one in France and some in Sweden. And there we could show for the first time that it's with a large variety of architects, they were able to do that. This was a very important milestone for the passive house development, to show that it's possible for many, many architects, 200, to do that. Well, I have added some numbers Alexander gave me. My numbers are in SI units from Europe. Well, I'm not so familiar with BTUs, but I have added here this. The kilowatt hour to BTU is a factor of 300 here, and the watt per square meter to BTU per square feet, it is a factor of about 3. And I have repeated that on some slides because I cannot recalculate this so fast. Thomas did. If you want some numbers in BTUs, please ask him. I only be able to give it in square meters and so on. Well, 1 inch is 2.5 centimeters. This I know, but not more. Okay, we started with single-family houses, and the first 10 years, most of passive house projects were single-family houses. But you see, there is a variety of architecture available. The next is, and this is with the Frankfurt Housing Company. Here, this project was in 2005. And was the first project of the ABG Frankfurt Housing Company. And why I emphasize on that, the architects, here you see them, these two guys, they come from Darmstadt, and they have had many experience in passive house before. And they went to the leader of the housing company, Frank Juncker, and said, well, this would be a good idea. Let us try it. And he said, well, I'm a lawyer, and I know you have to be careful with everything. But, well, you told me it should work. Well, you have the job. Show me that it will work. Yeah? So they had the chance to set up this first building, and they had the task to show a success. Yeah? So I think it's a hard job to do that. They had experience, and they worked afterwards. And by the way, as it was on a good site, a very good site in Frankfurt downtown, This project was sold out as apartments, single apartments sold. It was sold out within a very few months. I think 3 months they had it sold, and about 2 years later it was ready. Well, and afterwards the housing company decided to do all their new buildings as passive houses. So they adopted the knowledge to their own company. They have their own architects and engineers, and they have written from the first project well, and they adopted and they did it for themselves. And this was their first large project, 160 dwelling units, Frankfurt downtown. And meanwhile, they have about 10 projects like that ready. Well, and the second was as well ABG Frankfurt. They had they tried a renovation project. You already have seen this, Frankfurt Tewitzstraße, a social house out of the 50s after the World War. Well, and they said, try it and show us to come down from this 300 kilowatt hours per square meter a year to about passive house. So they managed to go down to about 17 with that project. Okay, this and that project we were in with monitoring, so we could doing measurements afterwards, and we saw that it's a very good success with that as well. Okay, this was the summary. And now the second step, Germany, non-residential and special use buildings. This is some office buildings, the Wagner office, Luteco, I will show some more in detail. The Engenerbahn office, Thomas already showed you. They have a concrete ceiling activation for heating and cooling. This is the special thing with that. The Wagner office building has a night flushing for cooling. In German climate, in summertime, it's during night it's so cool, air temperature goes down below 18 degrees centigrade, and so just by opening windows you can cool. And they did it with the Wagner office. I will not show you that in detail because of time. Well, and then I have some extra, there are some extra projects, supermarket, a fire brigade house, a swimming hall, hospital project. I will come into some detail with that right now. Well, school buildings as the first special kind of buildings you see here. This is a school in Frankfurt, for example. This is one in Munich, a Montessori school. Well, kindergartens are available like that. Gyms in Heidelberg and Munich, and office buildings. This is the Luteco in Ludwigshafen, and this is the Energon in Ulm. And these are some more. Marburg, Kölbe, Marburg, and this is a refurbishment renovation project in Tübingen. And this is the fire brigade house, and this is a factory, chemical production, and office building nearby. And these are some religious buildings, a church. And well, this is quite nice from Spain, a special building, a residential, but a special. They did the skeleton of this building, they did with old steel containers and added from outside. Here you see in some detail, they added polystyrene blocks, made it airtight. Here a detail, and well, installed a ventilation system and so on. And I think they had a very good success there. They have published monitoring data, and if you look, and you may Google their Eco Holistica in Granada, you may have some more details on that. It's quite nice, I think. Well, and then to get worldwide, then the question is to have it. What about going cold? You need better windows, more insulation, adapted ventilation system because of frost. Well, and the other side is going south, dry and hot. Dry and hot, and then humid and hot. And now I want to go into some detail with that project, what to do in summertime. Yeah, what to do if you need some cooling with residentials. Well, first of all, when going to cool, the question is, how cold should it be? What is comfortable? And here we took from the standard, this is from the ASHRAE and for the DIN 7730, a kind of range which is regarded to be overall comfortable. And this is relative humidity about 70% to 30%. And on the right-hand side, well, here you have the temperature, 20 degree, and here on the right is about 25. Or if you have drier air, the temperature is allowed to go something higher. Yeah, this depends crucially on humidity. Dry air is accepted to be a little higher temperature than humid air. Well, please note this is an operative temperature. This is an average value of air temperature and surface temperature. So sometimes it's misleading if you say, well, you have very hot windows and air cooled down to 18 degrees. So some people freeze or feel cold with that, but on the other hand, because of these very warm windows, you need this cold air to compensate somehow. So, and there it helps to have well-insulated outside shell and shaded windows to get surface temperature low as well. And then you need not to cool the air so much, to so low temperatures. Well, once more, you have seen this already this morning. This is because of the examination you have to memory. Now in U values, by the way. So you have it all: ventilation system, air tightness, good insulation, good windows, and so on. And these are the limit values in SE numbers, kilowatt hours. Okay, now for cooling. You have the same envelope, almost the same envelope, but you shade your solar load. In summertime, it's not a solar gain, but it's a solar load. Next is thermal protection helps in warm climate as well. You need not so thick thermal insulation in maybe Florida or here in wintertime, but you need some. Yeah, this is important. And I will show you the numbers later in the afternoon. Crucial is insulation on the roof. Yeah, because sunshine is coming from top. It helps to have the roof insulated, for example, by 20 centimeters of a layer of 20 centimeters. Sometimes we need not an insulation in the bottom in warmer climates, because no insulation in the ground helps for cooling in summertime. Yeah? Okay, but in principle, insulation helps as well for summer. Well, internal loads, these are the two imperatives: reduce internal loads and reduce solar gains. And for internal loads, well, you have to pay twice for electrical gains in offices. The first time you have to pay for the electricity to drive your computers, and the second time you have to pay for cooling the air conditioning to get the waste heat out. So it pays twice if you get the internal loads reduced. Okay, and then if you have some thermal mass internally, you can use that in temperate climates for cooling in summertime, just by opening windows. Okay, this is a basic approach for temperate, warm climates, where you can cool passive. Okay, some conventional hints once more. In winter, you do heating, you have internal gains to help. Well, and this is for non-residential. In non-residential, people are not present during weekend and during night. And therefore, you can stop the ventilation system at that time. In residentials, you leave them running all day long because people are, on average, always present. Yeah? Well, this is for that. And the next is for summer and hot and humid climate, you need some cooling. Passive cooling is mainly for non-residential consumption, but in office buildings, because of the higher internal loads, you need some cooling. And I will show you this concept of the Luteco, the concrete ceiling activation, and then go into some detail with the hot and humid. Okay, and afterwards I have some economic comparison of two building consumption. Well, once more, the concept is the same: good insulation, good airtightness, ventilation system, good windows, and airtightness. Well, just transported to the office building. Here, heating and cooling via the air, the supply air, is possible most time, in most cases. So that is because the heating load and the cooling load is very, very low. Thomas already had this number, 10 watt per square meter, or 3 kilo something for this in the IP. So for heating and cooling, you are able to bring the cool temperature to the building with airflow. As well, for heating, the warm air flow is enough for heating. Okay, but first of all, some special things with school buildings. I already mentioned. In dwellings, you have about 30 square meters per person available. School buildings and meeting rooms like this, when all people are there, you have about 2 square meters per person. Well, in dwellings, you use it all day long. In school buildings, only on the before noon or maybe to 18 o'clock in the evening. In dwellings, continuous operation. In school buildings, reduced operation during nighttime. You can save some electricity for the ventilation system. Here you have constant flow, airflow rate. Here you have, when many people are there, you have a very high airflow, and afterwards no airflow or very low airflow. Internal gains, 2 watt per square meter, and here, when people are there, up to 50 watt per square meter. Or if you start in the morning, coming from the weekend, you have to heat for 1 hour and to preheat the rooms, and therefore you need some high airflow and high power. This is here. Heating continuously, so only low power all the time, and here heating in the morning and not then. And the same with cooling. Well, and here you have a sketch. Only when people are present, you need to operate the ventilation system and the heating system, and therefore the loads then are high, and outside of this time the loads are low or even zero, and therefore the weekly average load here is about 4.7, so not so much. It's comparable to that of residential buildings. Okay, some basics about comfort. Well, you know, thermal comfort is temperature, not only air temperature, surface temperatures, difference of temperatures from head to foot, for example. This is a question of airflow, draft risk should be avoided. It's a question of relative humidity, and, well, it's a question of clothing and activity of persons. So if some are working hard, they need not so much heat, or they need some more cooling in summertime. Okay, well, and then if you start with passive cooling, you have to realize that this is the sum of many small contributions. So you cannot solve the problem with one thing, but you have to look at several things. Some of them I already mentioned. This is the electric efficiency, daylighting, computers, telephone, servers, and so on. The efficiency of hot water systems. So any heat load from a hot water tank, if this tank is installed inside the building, well, you have to cool this, the heat losses of that. You should use shading. Movable shading is preferred, but sometimes fixed shading is a good idea, especially for south-facing windows. Well, when I come afterwards to very cold and humid climates, the question is if you do a sun-blocking glass for all year long, because you have enough sun and not so cold temperatures in wintertime. You need not so much gains in wintertime. You can use a G value of 0.2 or 0.25 all years long, and you need not struggle with shading. Okay, if possible, you use night flushing, the passive cooling. You may use mechanical night ventilation without the heat recovery, or you do it automatically controlled. You can do some cooling during the nighttime with the heat recovery. Well, and if needed, add some additional power of cooling sensible or cooling and dehumidification. So it's latent cooling. And well, the last time the sun blocking glass. Okay, first short this project, this Luteco. You see here, the windows are not too large. It's not 100% glazing facade. And this helps us very much in that building. So the window size is designed, well, first of all, according to cost. This should be not a low cost, but an affordable building. They could only get about €9 per square meter a month for rent out this office here in that region. And therefore, they had a very limited, restricted budget. And one feature was then not to have too large windows, just because of money, but it helps for us. Well, and you see the shading, they have jalousies outside. Well, and they have a concrete core activation. And in summertime, they do a direct flow coupled to ground probes. They have 39 ground probes, 100 meters deep. And they just circulate the cool ground fluid to the concrete. And in wintertime, they have a heat pump there, and with the same, with the ground temperature during wintertime, they take the temperature up to about 22, 25 degrees, and then can go into the concrete here and heat with the same medium. And they have quite good seasonal performance factors of them. Yeah? You have to look for the heat pump, COP, and add the electricity consumption of the circulation pumps, and that's all. Okay, planning, very important. External shading and is a must, and internal heat loads have to be minimized. I already mentioned. Well, in that project in detail, the learning was you should check that you can operate and check the flow of the medium part by part of the building. Not all the building needs the same cooling power or the same heating power, because the use is different. Part of that building was occupied by a call center with very tight, very many people and very many computers, so they need almost no heating in wintertime, but they need some more cooling in summertime. And this part of the building has to be operated in different way from the other part of the building where an architectural office and a lawyer's office is in. Yeah? So you have to go into some detail with a control algorithm. The same for the shading. Only where sun is coming, the shading is needed, and not on the other side, because otherwise, when no sun is there, people want to look out. And and if a wind is coming, the shading has to go up, and so on. There is some German-spoken literature from that. You may have it. It's from Switzerland, and it's a very good thing. Here, some simulations of that building. We started cooling to get 26 degrees centigrade here, all summer long. And the shading is closed when the internal temperature was above 23 degrees centigrade. And you see here the solar gains are very much down. You see here in wintertime we need some heating, and in summertime we need some cooling. And in spring and in autumn the building is working completely passive, so only ventilation system is running. Well, if you would forget the shading, you see here, you would have a problem. You can cool, you have enough power with the concrete core activation, but the cooling power will be rather high, and you would have to check if your ground is going to high temperatures during several seasons. So you have to be careful. We are at low numbers of cooling power, and we have to check carefully that this is met, the goals are met. Yeah? Okay, just some hints. You may run your ventilation system with or without heat recovery and operate it as with a summer bypass in summer times. So get cool air into the building if you are not able to open windows. But you should check, if you run this system, you will have a delta T, a delta temperature added because of the waste heat of the fans. Yeah? But in principle, this is possible. Well, and what is possible for dry climates, for hot and dry climates, you can humidify the exhaust air in the heat exchanger, and therefore, and with that, you can cool down your incoming air. This is a system I also have seen here in Colorado 3 years ago. It's called Colorado. They cool down a heat exchanger on the one side with some water and use the evaporation energy to cool down the fresh air taken in. Yeah, it's a good idea, but it's working only with hot and dry climates. Well, how much time do I have left? 10 minutes, okay. Well, this is the summary. You have it on the CD. Just to repeat what I have already said. Well, generally spoken, you may need some cooling for office buildings, even in Europe, northern or in North America, or if you go some south. You see here typical building, here a residential building with the split devices on each apartment or each office. And you may know every day in summertime you have, or the power suppliers have the problem of a peak power during noon. Yeah? You see, because everybody is switching on his cooling devices at about 11, 12 o'clock. Yeah? Meanwhile, this is a real problem for the energy supplier, for the electricity suppliers. And therefore we had a project, it's called Passive On, a project funded by the European Commission to check what's to do against that. And now, if you go to that with a passive house conception, well insulated outside shell, well good shading, and so on and so on, you see here, you may need some extra cooling, but first of all, it's a small extra power for cooling, and second, and more important, the peak power is gone. Yeah? So you are able to cool down, to keep your buildings cool with a very low power and with no peak power problem. So this is, well, for example, if you go, by the way, if you go calculating costs for that, you know the peak power price for electricity is much, much higher than the average price. So if you can avoid the peak power, you have very much money saved. Well, and it's on the other hand, it's a question of security. Yeah, Alexander mentioned it before. If you get rid of peak power, you have the risk of failing of your supply system is not so high. Yeah? Okay. Well, the next point, what about humid climates? I said, well, in dry climates and not so hot climates, you can open windows during nighttime, but this is not true if you go to humid climates. And there we have Palermo and Torino. We have some towns in Europe as well where this is critical, but you know in America you have some of that more. And therefore, now some words about a very hot and humid climate. And this is a quite new project we had in the Shanghai region. There, a housing company, they want to build a hotel as a demonstration project, and they asked us if it's possible to get there with passive house conception. Well, what we have seen, to summarize, cooling and dehumidification with supply air should be possible. It's not realized, this project, so it's a theoretical statement, but we are quite sure that it will work. And what we see, heat recovery and humidity recovery, I come into detail with that, helps in winter and in summer. Yeah? And heat recovery, really, not only in winter you keep the heat in, but in summertime you keep the heat, the overheat outside. Well, what we see from the dynamic simulation, the internal gains are crucial. Well, we already had that. If you heat up your building too much, you have a problem. Shading is absolutely necessary. And if you have, well, thank you. If you have smaller windows, it helps because you need not so much shading. It's automatically shaded. Well, and there comes the idea of the sun blocking glass to have a G value of about 0.25 helps. And the idea came up because in China they fear about operating of the outside jalousies. Yeah? They say, well, users are not familiar with that, and they eventually will forget, and then the internal temperatures will be high, and the cooling system will not be able to get it out. And therefore, one idea was to get here in with a sun blocking glass. Okay, this raises the heating demand in wintertime, that's clear. You have not so much gain, but helps in summer. And as we do not have so hard winters there in Shanghai, it's about 0 to 5 degrees centigrade minimum, well, it should work. Well, now the graph, maybe you can see it a little. The cooling and the humidification thing. You see here, this line here is the building. And we divided the system into two things. The left-hand side is a central unit on the roof, for example. Air coming in is moving through a heat exchanger, summer and winter. And then, if needed, there is a cooler for dehumidification. Yeah? So first, well, let us begin with that. You come out of the apartments with a temperature of about maybe 25 degrees. So this is the condition from the waste air going out. And this waste air of 25 degrees helps to cool down the outside air of maybe 35 degrees to cool down somehow. And afterwards, you do the dehumidification to get less than 12 grams per kilogram absolute humidity. And with that air, you go to the pipes in your building. And this 12 grams per kilogram, that helps not to get any mold in all pipes. Yeah? Well, and then with that air, preconditioned down to about 22 degrees centigrade, it will heat up something when going through the building, but not very much. Well, and then in the single apartment or maybe office, part of the office, you install a conventional split unit, or the internal part of the split unit, like here in the hotel. But what is important, you drive it not with 6 times air change rate per hour, but you may only use 2 times per hour. And therefore, the noise emission of this device will not as high as a standard split cooling device. And so we think the acceptance of this low power cooling device will be much higher than before the very noisy cooling devices. Yeah? Well, and now some data out of the simulation. You have here this gray one is the outside temperature. The violet one is the solar gains, and the yellow one are the internal gains. And here, this is cooling power, and the blue one here is the heating power in wintertime. And you see it's quite similar than before in the other office building. You have in wintertime some heating, you have in summertime some cooling. Well, and the violet below here, this is the power for dehumidification, for drying the air. So to have the whole cooling power, you have to add this both. Well, and what you see here, in spring and in late autumn, you have a kind of neutral zone. You need no cooling and no heating. Yeah? It's working purely passive. Okay, well, preconditions, as I mentioned, internal gains have to be reduced as good as possible, and shading is absolutely needed. Thank you. Okay, here this is the neutral zones. And you see here the neutral zones comes because only in mid of summer I need to cool to get 26, and here in between that, coming from 20 in winter time going up to 26, in that time I need no cooling, no heating. I leave the temperature as it is. Well, you can discuss about having not 26 but 25 degrees centigrade, but this is detail. It's your decision. It will not change very much if you go to 25 or maybe 24 degrees. Well, if you would go to very low summer temperatures, well, you would have some extra power. Well, here, the sensible cooling and the latent cooling, you see the humidity recovery helps. Yeah? The dryer is not only an active dryer to cool down, but together with the, just throw it away before it. Okay, if you would not be able to shade, you would have a problem. Yeah? Did economic calculation. It is, thank you. It is in Germany, and my colleague, she did a comparison of the low energy house according to the law 2007, the same for the law 2009, and for passive house. And you see here, for the low energy house, we had standard U values, here a little better. We had in summer cooling devices, split devices, and a standard gas boiler, here a condensing gas boiler for heating, and the split cooling for cooling, and internal gains 5.7 and air tightness 1.5. And a standard lighting design, or no lighting design. For the passive house, we have these better U values, or you already know. 3-pane glazing, a concrete core activation, as I mentioned before, and that is driven with ground probes as well as before, with a heat pump for winter time and a direct coupling for summer times. And therefore, you have only one system for heating and cooling there. Okay, well, and you have a ventilation system, clearly. And in addition, you have here lower lighting, lower power installed for lighting, because of a special light design. So you will get this only realized if you have a special light design. Well, and now she got the numbers what is the cost for this and that. By the way, she added the cost for extra planning, and you will not see that on this scale. Yeah? It's just diminishing. The cost for extra planning is about zero. Yeah? Well, but you see, the extra investment goes up and the costs are higher, that's clear. But if you look at the annual payments, so if you look for the total costs, you see here, well, here below that, this should be gray. These are the investment costs calculated via dynamical calculation, including interest rate. These are higher. I will come to the end, but I need some 2 minutes. Okay? Well, what you see here, the investment goes up, but the payment for energy is going down. Yeah? The total, so including the total life cycle costs, are going down. Well, this depends on interest rate and this and that, that's clear. But this as a general outcome of that, today we have rather high energy prices and low interest rates. Well, and this is clear. It's better to invest money for a better building envelope or better technical systems to save, on the other hand, energy consumption. So this is a chance we just have nowadays. Low interest rate and high energy prices. This is which helps us for argumentation. Well, and what is really important, this is the keyword, this total cost. You should add both together. Okay. Well, PHP, we do it tomorrow, and Thomas does this just as a hint. Now, in very short words, some hints about newer projects. Gyms and supermarkets, markets, please look at the Puzzlepedia. We have documentation there. I want just to show you a quite new project, a swimming hall in Bamberg, and a hospital, which is project just starting now in Frankfurt. This swimming hall, here you have impression, it was just opened a few weeks ago. And you may have on this website some information. We will do monitoring there and look what's going on. But in principle, you see, you need not only to look at the building envelope there. One crucial question is, what about the humidity of the inside air? Standard swimming halls, they reduce the humidity to very low numbers to avoid condensation at windows. But we have very good windows, so we allow for higher temperatures. We have higher temperatures at our windows, and therefore condensation will not occur so early, and therefore we can allow for higher internal humidity, and this saves cost for the dehumidification. Well, and then I will not go into detail with that. You can apply every kind of power supply, and one of that is a good heat pump system to use energy twice. Well, the next project is a hospital, just starting the project. You see here, it's an old, well, yes, it's an old house here out of the 60s, very bad situation, and the city of Frankfurt, they need to do it new, and they asked us to make a conception for that. And once more, here, the envelope, this task is already done. Yeah? We know about the envelope, what we will do it. So the standard where people are in their beds there, that's no problem. But what we now have indicated as a task is to look for the special energy flows. What you use, what electricity you use for this and that. And this is a task. We are just at the beginning. Well, and maybe we could share knowledge in 2 years or 1 or 2 years. and have a look what's going on. This just as some impressions, and with that I am come to an end. Thank you very much.